All right, let's look at how to do a pulley, how to model a pulley inside workbench LS-Dyna. So what I'm gonna do today is I'm going to model something that look like these illustrations here. Basically, I have a two pulley linked together. On one end, I'm going to apply a 50 Newton force. On the other end, I'm gonna use a body to ground spring, right? That's going to sort of resist that force. As you can imagine, what will happen is that should be able to see a pulley action that pulls the spring upwards, and the spring the cable here will go down. So I want to sort of model this basic illustration. So the way I'm gonna do that is to use something to look like this. Basically, I have four beams shared together, no shared together, and they're gonna be treated as the same body. On one end is my force end, on the other end is my spring end, and that sort of depicts what I'm gonna do with this model. Okay. All right. So let me go ahead and exit out of space clean, and then let's look at the model together. All right. So in this model, right, you can sort of see, right, I have just a single body, right, with a 0.2 with like around here. Let me change this to inches. But about a quarter inch of beam cross section in here. The cross section is really not relevant because I'm mostly just doing it for demonstration of the beam purposes, demonstration of the pulley actions. The way we're gonna do this, right, is that um, let's go ahead and first of all, let's go ahead and mesh the beam. I think that's the first thing we have to do. So what I want to do here is let's create a sizing object, which is going to basically select all four bodies. Oh, excuse me. I'm sorry. I'm gonna go ahead and select the edges. Apologies. And I'm gonna use sort of number of division, change that to 1, and I want to make sure my global sizing is very high. This way, what will happen is that I'll create 4 different beam elements in here, right? So as you can see, I now have a total of 4 elements in the model, right? So element 1, 2, 3, and 4, each of them has a division of 1. Then ensure we have 4 different beam elements in here. Now what I want to do next is that I want to make sure this node right here is always going to have the number that I want it to have. So what I'm going to do here is that add a invariant node numbering, and then I'm going to control this node right here. Oh, oops, sorry. I control this node right here, and then make sure the number is always 1. Now the reason I do this is because I want to make sure when I generate the body to ground spring, I can always rely on the node number 1 to do so, and I can double check that this is actually the case by selecting this node right here and check my number, which is exactly correct. It's node number ID number 1. Okay. Now once I finish, this is done. The next thing I want to do here is to look at basically changing the section of these beam to truss. Now the reason I do that is because what we're going to do to generate the pulley action in Dyna is to rely on this card, element beam pulley. So this is the key card we're going to be using to generate the pulley action, and it's actually so well done in my opinion. It's very easy to do, and it's far easier to model than, say, for example, in Ansys Mechanical, where the modeling of pulley becomes a lot more complicated, and I've tried that several times really without creating a dummy model that I'm really happy with, right? So this model really requires just a couple things, right? They require 2 different truss beam elements. So the truss beam elements are essentially beams with an out form of 3, right? Which is what I'm about to do next. And then what we also require is a pulley node. Now what this pulley node does is that it has to be a node that is in the same location as the node shared by these 2 truss elements. So if you look at this first sentence in the remarks, right? Truss element 1 and 2 should share a node which is coincident with the pulley node. The pulley node should not be on a beam element. So what that means is that in order to generate a pulley node, right, we have to use the node keycard to create a node in space, but we want to make sure that node is in the same geometric location as the node that's being shared by BID1 and BID2. Now, if you didn't follow any of that, I'm about to show you in the example problem, which is why example problem are so much more valuable than just reading the documentation, right? Reading documentation is always going to be pretty dry. So let's look at how we do that, right? So first thing we want to do, as I mentioned before, is that we want to make sure these beam elements are truss elements. And the way we do that is to make sure we assign outform 3 to them, right? So outform 3, we're going to generate a section card, and then make sure this whole body is assigned to it with an outform of 3. You see that truss right there? That makes sure that these beam section are going to have an outform of 3. All right, that's the first step. The second step is to generate the pulley card. So let's go ahead and do that. So I'm going to insert a command object right there. And then I'm going to use element beam pulley. Okay, so the way you want to write into these cards, right? Like I mentioned, I always have these dummy because I have a library of cards that's already ready to go. What I usually do is that I would just go in here and then use a dummy model and then just sort of just copy that over and modify it as I need to. So let's find my element beam pulley, which is right here. I'm gonna copy this card over. Now FD and FS are your friction coefficient, right? It's something that we just want to modify a little bit. The other two parameters shouldn't matter too much. And these 3 parameters are my beam element 1, beam element 2, and my pulley node, which is what I'm gonna manipulate and generate right now. Okay. All right. So let's take a look at the documentation real quick one more time. Right. So FD is my Coulomb dynamic friction, and then the other one is my Coulomb static coefficient of friction. So I think I probably want to reverse these 2 numbers. We'll make them both 0.1 in this case. And then I have to basically find the element ID of my truss element, right? So let's look at my model. Look at this very simple model, right? I have truss element 1 and truss element 2. Truss element 1 has an ID of 4. Truss element 2 has an ID of 3. So I want to go in here and say BID is 4, BID 2 is 3. Now, then next, what I want to do is create a node ID, right? That node ID is not this node. This node right here is not the node ID I'm looking for because that's the node that's shared by the truss element. What I want to do is to create a node that's in the same geometric location as that one. So the way we do that is to use a node element, but I'm going to change the units to millimeter now, right? And then to put these XYZ location onto that key card, right? So the way you do that is to use a node ID. So let's go ahead and copy, because I have 2 different pulley elements, I'm going to go ahead and copy this onto the other side, and then that's okay. Take a look at the other two truss element first before I do the pulley nodes. So this is node ID 1, and this is node ID 2, right? So all I have to do is go back to my card and change this to, guess what, 1 and 2. Now what I have to do is now define the pulley node. Okay, so the pulley node, what we're gonna do is to use a node card to do so, right? So the node card. Let me see if I can find the documentation to show you guys real quick. Right, so if I use the node card, which is going to be way down here. Oh god, okay, sorry. Let me see if I can find it quickly. It's a little bit harder because I can't really search for too many nodes, too many call off of node cards. So N right there. So I'm gonna look at the node cards, right? So node cards basically asks us to define a node number, then define the XYZ coordinate of that node number. Simple enough, right? And then TC is my translator constraint. TRC is my rotational constraint, which in my case, it's always going to be not constrained whatsoever, right? So because I already have this ready to go in my master file, so I'm just going to create my master file here, and then I'm going to copy this over. And then you can sort of see I already have it ready to go. So I'm gonna copy this into my master model, right? So I have my node card and another node card. I'm gonna call this the ID 903 and 906 instead, right? All right. So this node right here, what I need to do next is to find the geometric location of this node, which has the XYZ 12.7, 25.4, and 50.8, which is exactly what 12.7, 25.4, 50.8. So node 903 is going to be coincident with the node that's shared between beam 4 and 3, which is this node right here. So node 903, which I just created using the node keycard, is going to be in the same location as this highlighted green one. And then this one right here is going to have same X and Y and different Z. So 12.7, 25.4, negative 558.8. So what I want to do next on here is that I want to change this number to negative 558.8. Right, make sure the keyword is aligned. So this node right here is going to be 906, and 906 is going to be aligned with element ID 1 and 2 in the same location as the highlighted green one. All right, that's it. These two nodes which I just created in a text file, even though you can't see on the GUI, is going to be referenced by the Pulley card. And the last thing I have to do, as you can imagine, right, the Pulley node cannot move, as all Pulley wheel wouldn't move. Right? So what we want to do next is that to use a boundary SPC card to lock the node down. So this is a standard boundary SPC node card. Basically, node 903 and 906 is going to be fully locked down. The constraint XYZ, RX, RY, RZ are all 1, which indicates that the nodes 903 and 906 are 100% locked down. And that's how we make sure we have the Pulley action. So quick review. We created our element Pulley. We reference the node we just created in here as a Pulley node, which is coincident with the location of the node shared by the two truss elements, right, beam elements. And then lastly, we're going to lock the 903 and 906 nodes down because those are Pulley nodes which cannot move. And that completes the definition of the element being Pulley, right? Now what I want to do next is to add a force onto one side. So I'm going to add a force onto this vertex. And then I'm going to add a negative 50 Newton force. Right, and on the other end, what I want to do is to add a spring. Remember the back to the ground spring, right? So element discrete. This is a discrete element. So to generate a discrete element in the keyword file, right? What you have to do is to create a part, a section, and a mat card out of thin air, essentially. So what you do here is that I'm gonna create a part called 100. Which is going to reference the section of 100, which is also going to reference a mat ID of 100. Right, the mat ID is a mat spring elastic, which is a linear spring with the K value of 0.5 Newton per millimeter. Right, so this creates the discrete element. This creates a part which is going to be used as a discrete element, and the discrete element is created by using the element discrete card down here. Right, so element discrete is going to have the ID 101. Reference to the part ID 100, and it has a node ID 1 and a ground of 0. So that's okay. The element discrete. So you can sort of see what I did, right? So if I would look up element discrete inside the documentation, you can sort of see, we're looking for a part ID which is 100. We're calling the first node, which is node number 1, which is what I created. And then if we set node number 2 to 0, we have a back to the ground spring, right? And that's essentially what we did. And EID is the discrete element ID, which is 101. Right? So if you look at what I did here, I created a discrete element 101, calls for the part ID 100, and then it's going to reference a node number 1. Node number 1 is going to be this node, which I referenced here, right? And that's going to have a back to the ground spring that's located at node number 1 with a K value of 0.5 Newton per millimeter. And that's essentially what we're doing here, right? So if that was hard to follow, just remember when you create a discrete element, you have to create a part, section, and mat, and then create a discrete element. And that discrete element is going to require you to reference a node value, which allows the spring to be attached. So if you assign two different node value here, you'll put a spring between those two nodes. If you do one of them value with another one at 0, you're going to create a back to the ground spring, right? And that's all really what we have to do. It's pretty easy to do in the end if you think about it. Okay, and then the very last thing that I need to do, I guess I need to go ahead and define a termination time first. Termination time in this case is 1 second. I'm just going to run the analysis for 1 second. It doesn't really matter. It's a very fast analysis, right? Because we only have 4 elements in the model. And the very last thing what I'm going to do here is I'm going to create a database card, as I always do. The database card is going to basically, in this case, allow me to probe some additional information related to the pulley and related to the beams, right? So I have an element pulley out, database pulley out, which is going to collect some information about the pulley, just because we're doing a pulley analysis. We can also add a extended binary database card with a beam IP of 4, and that's going to give us some information about the beams, which we have in this model, right? Because in this model, all we have are beams and pulleys. We don't really have any solid, we don't have any shell. So most of the default database card is not going to do anything for us, which is why I'm writing out some database card here. Okay, so let's double check our model, right, before we write out the input file. We have a beam model, which I'm using. I'm meshing with just 4 different elements, right? I'm making sure this node right here is 1 because I'm using that to create a discrete element, a bi-ground spring here. And with these 4 other elements, I'm creating a pulley, right? Pulley is going to reference these 2 beams and put a pulley node here. And it's going to reference these 2 beams, put a pulley node here, which is essentially what we did here. The beam itself is going to see a force of 15 Newton here, and it's going to have a by-the-ground spring that's going to be over here, right? Now remember, these 2 nodes are fixed in place with the boundary SBC node card right here. And then the beam itself has an element formulation of 3 because the beam pulley card requires to use truss element to do the model. All right, that should be everything, right? Let's go ahead and do a save. And let's write out the input file. I'm gonna call this the input demo, right? And then let's go ahead and select the input file, and then let's go ahead and solve it. And then you should solve instantaneously, right? Because it only has 4 elements in it, so there's not much solve time to begin with. And then let's go ahead and write out, go ahead and look at the input file in here. So let's look at the results together. Okay, so in this case, what we have is this is the results. I'm gonna run the animation real quick. You can see this is the spring, and this is over here is the 15 Newton forces, right? And then what I can also do here is to sort of look at things like axial stress. Let's look at axial force resultant, right? So we'll have about 15 Newton of force here, a little bit less over here. We can also look at the force resultant right here. So force around here around 36 newtons, rest of it is going to be on the spring, right? And what we can also do is look at the binary files, and then let's check pulley out right here. And then I have 2 different pulley. I can check things like the pulley forces, right? So the pulley also experiences around 15 Newton of forces, and on the other one, it's actually going to be slightly higher. And I think we can also check the spring if we wanted to, which I'm not going to do in this video. Okay, but that's basically the idea because it's a very simple model. You know, I can change the spring stiffness, which is going to reduce how much this thing moves. But basically over here, we can see these 2 nodes don't move, and the whole thing behaves like it's a pulley, right? Which is what we wanted to accomplish in this model. All right, and that is the step-by-step tutorial of how to set up a pulley action inside workbench LS-Dyna. Remember, we can use the same technique and apply the same technique to a much more complex model, which is going to that may contain a pulley element, right? That's the whole idea of upscaling our simulation capability, is to be able to do the individual things by building a very simple example model and incorporate that into a much more complex model. Because a more complex model is just a lot more combination of simple things, right? So mastering the basics is how we can learn how to do more difficult stuff. All right, thank you.